Okay, so we are looking at question 12 over here. An object has an initial speed u and acceleration a. After traveling a distance s, its final speed is v. The quantities u, v, a, and s are related by this expression. Now we know this expression we can find in our data booklets, and all of these are dealing with uniform accelerated motion. So which of the following includes the two conditions necessary for the equations to apply? Going through them, we're going to have C, because A has a constant magnitude and A has a constant direction. These formulas always apply to uniform acceleration. So that is C. Good. All right, going on to question 13. Just pull it up here. Question 13. It says the graph shows the variation with load F of the length L of a spring. Which of the following expressions gives the force per unit extension? So we're going to get a Newton per meter to the negative 1, the spring constant of the spring. Now, this is looking at a force per unit extension, so we're actually looking at a point where you've got a directly proportional relationship here. And in these over here, it would be this one over here, because we've got a systematic error taking place basically there. So if we want a force per unit length, we want to take the slope of that over that. So that this would be the change in force, and this would be your change in length. So that would be F2 minus F1 over L2 minus L1. We're actually looking for the slope of the graph when it says a force per unit length, which would be given by D. Okay, close that, and we're going on to 14. 14. Alright, now firstly let me just make the important point that whenever we're dealing with a situation where you've got some object and something happens to the object, either collides or there's an explosion and something changes, we need to be thinking of conservation of momentum, conservation of P. Alright, remember P is the symbol for momentum. So we've got a rocket is moving through space. The rocket engine ejects a mass of m of exhaust gases in time t. The speed of the exhaust gases relative to the rocket is v. So we get here something like this mv in that direction. Because this is a isolated system, it's all happening within the rocket, there must be conservation of momentum. Therefore, the momentum before must equal the momentum afterwards. So in this direction, there's a change in momentum in that direction. So in this direction, there must also be a change of mv. And it would be minus because it's in the opposite direction. Now, which of the following expressions is the magnitude of the force exerted by the rocket? Now, we've got a change in momentum is equal to Ft, which is the impulse. So F is equal to change in P over T. So it would be, we've got the magnitude of the force exerted by the rocket on the exhaust gases. So this is going to be in the this is going to be in this direction, so it's going to be your mv over t would be your answer. So it would be D. Okay, good. So remember that, this thing about conservation. Whenever we're getting some sort of collision, some sort of change in a system, think of conservation of momentum. Fine, going on to 15. We have here an object is suspended from a roof of a lift. From a roof of a lift elevator as shown below. When the lift is moving upwards at a constant speed, the weight of the object is W. and the mass is m. Now remember, weight is equal to mg, or m times the acceleration. Now when it's going at a constant velocity, we know that we've got it's mg because the acceleration due to gravity is g. That would be its weight. Now, which would be the following correctly gives the mass and weight of the object as the lift is accelerating upwards. Alright, now the mass of an object never changes. You have the mass. This is a property of the object itself. This never changes. You can find the mass of an object on the moon, on Pluto, on the other side of the universe. It should be the same wherever you measure it in the universe. But the weight does change. It depends on the mass times its acceleration. So if the acceleration is now greater, alright, it's now greater, it's going upwards, then it would be greater than W. And so it would be 15b would be the correct answer there. Going to 16. Now this one I had a little bit of a difference with the mark scheme, but the actual answer for this according to the mark scheme is 0. I think it should be C. This sometimes happens. You just got to give the best answer. But the graph below shows the variation with displacement x of a force F acting on a body. Force F always acts in the same direction as the displacement. At point P, the displacement is x and Fq. Which of the following gives the work done by the force? Now remember, work is equal to F S cos of theta, where theta is the direction. Now in this, because it says always acts in the same direction, that theta is 0, so that becomes 1, so it's equal to Fs. Work is equal to Fs. It's actually the area underneath here, because your force is increasing and your x is increasing. Now as the displacement increases from 0 to x and then returns to 0. Now because they're saying it's returning to 0, basically what's happening is you've got something like that. As the displacement increases from and then returns to 0 again, we've got that. That's why they're saying that this is the answer here. I think that this is because work is not a vector, and therefore you are still doing work all the way through. So I would think that answer over there. I'll get back to you on this one. I'll discuss it more, but the answer according to the mark scheme is that one there. Okay, going on to 17. This is an interesting one. 17. Water flows out from a tank down a pipe as shown below. The pipe is always full of water. This is a very important statement for answering this. Which of the following gives the change in the kinetic energy and the gravitational potential energy of the water as the water flows down the pipe? So the thing with this is that what you've got to realize is that if this is always full, the amount of water coming out must equal the amount of water going in. Alright, because if it isn't, then there's some space if it's going faster. So actually the velocity in this must be constant, and therefore the EK must be constant. But the potential energy is decreasing. So for 17, we're going to have a constant kinetic energy, but a gravitational energy decreases. So the answer is A. Okay. Going on to 18. Engine X is stated to be more powerful than engine Y. Which of the following is the correct comparison of the engines? So we think of powerful. Remember, power is equal to work over time. It can do, when something is more powerful, can do more work in a smaller amount of time. It's amount of energy per unit time. So this one, let's see which works with that. Engine X produces a larger force. Not really going into the definition of work. Engine X produces more useful energy. Okay, not really going into. We've got to work with this definition here. Engine X produces more useful energy per unit time. All right, so this is definitely the correct one. All right, so it's the per unit time. Go to your definition of power. All right, so we got that one. Maybe I can pull both. No, I can't. Alright, so here we are. A particle is moving around the circumference of a horizontal circle of radius r with a constant speed v. So it's going in a circle at a constant speed v. Obviously the velocity is changing, but this magnitude of the speed. Which of the following is the acceleration of the particle? I hope all of you would straight away be able to say that. Because it's a constant velocity, there is no, it's not accelerating in the direction of movement, but it's accelerating inwards because of the change in direction. Alright, so it would be that over there. And then question 20 is also related to circular motion. Let's just bring it up here. Question 20. We have a fairground ride. A car of mass m travels on rails around a vertical loop of an effective radius r. At the top of the loop, the speed of the car is v. The car stays in contact with the rails as shown. So we have a resultant force that is acting down here would be your centripetal force, which is C is equal to mv squared over r. Now, the force reaction is going to equal that mv squared minus r minus the mg. Now the reason for this is that your reaction force has to supply the extra force because mg is working in the same direction. You've got mg there. That provides some of that. So this is the resultant force that actually is acting on this. So if I change this formula around, my force reaction plus mg is equal to mv squared over r. That's a resultant force that's acting down. Some of it is made up of mg, some of it is made up of the force reaction. Together they make the force that is causing the circular motion. So it would be this one over here. It would be 20A. Okay, so that ends those multiple choice questions. Remember the important thing, always when you're doing this, read carefully. And I hope I've shown that. Read carefully and look for the law or principle or formula to base your work upon. Okay, thank you very much.